Okay, so you've done some ideal questions, you've done some combined questions, but what about when they're both on the same assignment? You don't know which one to use. You've got to be discerning and trying to figure out which formula are you supposed to have. Now, ideal is always looking at a situation that does include moles. So that's a giveaway, and it's always looking at a situation right now. What is the gas like? Whereas remember, combined, that's always looking at a before and after situation. So ideal, if we remember the formula for that one, that is just the PV equals nRT. And don't forget that that R is 0.0821 atmospheres times, well, let's see here, atmospheres times liters over mole Kelvin. Whereas when you're dealing with combined gas law, that's over here. That's going to be PV over T equals PV over T. 1, 1, and 1 for the before, and 2, 2, 2 for the after. So that's what we see taking place with these two formulas. So let's look at the first question. Okay, right away, it says 4 moles. Now, I could be wrong, but it's already talking about moles, so I'm guessing it's probably going to be that one. And whenever we have one of these types of problems, there's only one pressure, there's only one volume, there's only one temperature, there's not two of anything. And I look, I see a pressure, I see a, yeah, it's got to be this one. So I'm going to go ahead and I'm going to write the P where the P goes. I'm going to put 5.4 ATM. I'm going to fill in the liters, 120 liters. I'm going to go ahead and fill in the, well, I don't know moles, so I'm going to put N times 0.0821 atmospheres times liters over mole Kelvin, the craziest unit out there, times temperature. Oh, good grief. I do know the moles. It's 4 moles. Some of you are screaming at me while I was doing this problem. So 4 moles. Sorry. That's a 4. We don't know temperature. So now I go ahead and divide both sides. I put 4 moles here. I go ahead and put 0.0821 atmospheres, liters over mole Kelvin. Same thing on this side. 4 moles. 0.0821. I think I've said this on other assignments, but really, don't just watch me do these. Pause the video and try these out on your own. See what you get. Now, I put this all together in the problem. I get an answer. And I end up getting the number, oh boy, already here, 1973.2. But over here I have 2 sig figs and 2 sig figs, so I can just keep those two. The 7 is going to round things up. So I'm going to get 2,000 Kelvin, but I can only have 2 sig figs, so I put a line there. That would work. Or I could do 2.0 times 10 to the third Kelvin. That would work also. Okay. Number 2, it says, we have a new problem. Oh, yuck. Okay. Now, in this problem, it shows it's, well, first of all, we know that if we were using ideal for this problem, this does not work. KPAs are not good for the type of R we have. So I would have to change that into atmospheres. But let's just see. Oh, look at this. Initially. If it's talking about initially, guess what? You're probably going to use this type of formula here. It's before and after. So initially have this stuff, and then I heat it. Okay, there we are. We're going to be using combined gas law. Now, you don't have to do this, but I do like things in atmosphere, so I'm going to convert this. So I'm going to go over here for 84 kPa over 1. I want to get rid of kPAs and turn them into atmospheres. So I'm going to do a little conversion factor. I know that 1 atmosphere is the same as 101.3 kPAs. I'm going to go ahead and figure out my math. 84 divided by 101.3. I'm going to find out that when I'm doing this problem, I'm going to be using 0.82922 atmospheres. Now, be aware, sig figs, I know this is 2 sig figs, and this number carries with it 2 sig figs, but I don't want to cut it too short yet. I want to keep that full number when I'm doing my math. At the end, I know that this contains 2 sig figs, though. So we already said this is before and after. So before initially, it's got this, 0.82922 ATM. There. Initially, it's at, what's the volume? Oh, assume the volume of the container is constant. Okay, so I'm going to put it in there for now. The temperature, it was 350. Now, remember, I got to change that into Kelvin. So that's going to be more than that, 623 Kelvin. Afterwards, this one always throws people off. They just see 230 and you just start robotically adding 273. No. I say I heat it an additional 230. Aha. So it's 350, add the 230, and then add 273. This is going to be 823 Kelvin now. Now we don't know the pressure. That's what we're trying to figure out. And the V2, remember, the volume stays constant, so those two can cancel out. Now I've got to go ahead and get rid of this 823 Kelvin. So I write it here, 823 Kelvin, put it over here. These two cancel, and I've just got to multiply these two numbers and divide by this. And when I do that, I'm going to get an answer of, 1.13535 atmospheres. But remember, I can only have 2 sig figs, so it's just going to be 1.1 ATM. And then my answer is all set. Next, number 3. My car has an internal volume of 2,600 liters. If the sun heats my car, oh no, your sun has a temperature of 200 Celsius. It's above boiling. This is bad. Okay, so this is another one of those cases like, we just throw some numbers out there. Bad numbers to choose. But let's just pretend it was at 200 Celsius, and now it's at 550. I'm not sure. Maybe your car would be melting, but we're going to pretend the car is staying stable. What will be the pressure inside your car? It's not good. This is really bad. I know. Only a science teacher would laugh at something like this. Okay, you're just like, I don't know. Just give me the answer. Let's just assume the car... First of all, assume the car does not melt and assume the car's volume stays stable. It stays at 2,600 the whole time. So I can just cancel that out. The pressure originally, assume the pressure was initially, yuck, millimeters of mercury. I can keep that. That's fine. But I like things in atmospheres. And fortunately, I know that the conversion factor, 760 millimeters of mercury, that is equal to 1 ATM. So, hallelujah, that's an easy one. So initially, I'm going to write 1 ATM. The volume, yes, it's 2,600 liters. Over the temperature, it's 200 Celsius, which is really 473 Kelvin. Equals, afterwards, what's the new pressure inside of your melting car? Pressure 2. Volume 2 is 2,600 liters. The new temperature, it is now 550. It didn't heat an additional. It just is 550. So that is 823 Kelvin. Okay. I can go ahead and cancel those. Just leaves me with fewer numbers to punch in my calculator next time I get something wrong. 823 Kelvin. 823 Kelvin. Cancel. Cancel. My new pressure is going to be, 1.739958 ATM. Okay, that's gonna be my new pressure inside of my melty car. Sig figs. This only has 1 sig fig, so it's actually going to turn to 2 atmospheres. Now the next part of the problem says, "Hey, how many moles of gas are in my car?" You're like, "Whoa, wait, I don't. Why are we asking that?" Well, I have all this data up here. Now, assuming my car doesn't melt, I'm just heating the car up. It's all closed up. The moles of gas before and after should be the same. So I can use these numbers to figure out how many moles of gas I have, or I can use these numbers. Now remember, you're like, wait, I don't have that. This P2 is this one. Remember, we already have the pressure. I'm going to choose to use the beginning numbers, and here's why. I calculated this new pressure. What if I goof this problem up wrong, and if I use this new number in this new problem and get it wrong, that'd be like a double wrong. Whereas I know these numbers are all correct. So I'm going to do a PV equals an RT type of problem with this one. So the pressure originally is 1 ATM. The volume is 2,600 liters. The N, that's what we're trying to figure out. The R, 0.0821 atmospheres, liters over mole Kelvin. And I'm going to multiply that by the temperature, which in this first part of the problem is 473 K. Now, if I use this, and this with the same, I'm going to get the same answer either way. You can do the problem either way is fine. Okay, so I'm going to divide this side by 0.0821 and 473. Oops, 473. Divide this side by 0.0821 and 473. Cancel, 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 cancel. figure out the math on this, and when I do this, boy, I'm going to get an answer of 66.95 moles, which with sig figs is going to turn into 70 moles. Okay. Oh, I should say, well, we'll come back to that later. Let's take a look at the next one. So that's how that one was done. Okay, 70 moles. And again, I could have used these numbers to figure it out with this, gotten the same answer. Okay, number 5, I got a balloon, a toy balloon, versus, I don't know what, if they're all toys, right? It has an internal air pressure of 1.25 ATM and a volume of 2.5. I take the balloon to the bottom of the ocean. I'd like to be under the sea. And the pressure is now 95 atmospheres. I've been crushed as a human, but I have a balloon down there that I'm observing. What will the new pressure of the balloon be? Okay, well, there's a second problem. Let's pretend that doesn't exist right now. Let's just do the first problem. We'll get to that second one later. Okay, what will the volume of the balloon be? So we have a before and after. I've got the balloon at the top. I take it down to the bottom of the ocean. So the pressure beforehand was a 1.25 ATM. The volume of the balloon beforehand is at 2.50 liters. This is another, it doesn't tell me, well, it does, some of you looked ahead to the problem. It says, hey, how many moles of gas does the balloon hold if the temperature, it doesn't tell me if that's before or after. So I'm assuming the temperature is remaining constant. I know the temperature at the top and the bottom of the ocean should not be the same, but we're going to assume it is. So we can just cancel temperature out. We don't have to worry about temperature. So PV over T, which, well, I guess we can put it in there if we want. Okay, equals. Afterwards, the new pressure is 95 atmospheres. And we don't know the new volume. What will the new volume be? V, 2. And again, we can say this is 285 if you want to. So the two temperatures cancel. Let's just get rid of those. I need to get rid of 95 atmospheres, so I put 95 ATM here. And I put 95 ATM here. These 295 cancels. And I'm just going to take 1.25 times 2.50 divided by the 95. When I do all of that work, I'm going to end up getting an answer of the volume being 0.03289 liters. With sig figs, it's going to be 0.033 liters. That's going to be my answer. But then we get to that last problem. It says, hey, how many moles of gas does the balloon hold if the temperature is 285? So here's another one of those situations where I've done a combined, but I can go back and do an ideal. So PV equals nRT. So in this situation, I can use all of these numbers at the beginning, or I can use all of these numbers at the end. I'm going to choose to use these numbers, and the reason why is because I know for sure this, this, and this. Whereas this new volume that I just calculated, I'm pretty sure I did it right, but what if I did it wrong? I don't want to plug that number in there. So for my pressure, I have 1.25 atmospheres. My volume originally is 2.50 liters. My N, that's what we're trying to figure out. The R, that's 0.0821, and the temperature is 285. I'm going to have to squeeze that in there, 285 Kelvin. So I'm going to divide both sides by 0.0821 and 285. This side, same thing, 0.0821 and 285. And now I can do all of my math. And when I do that, I'm going to get an answer of 0.134. Now this is kind of interesting. Check this out. In the first part of this problem, my answer only had 2 sig figs because I was using all of these numbers. But in this second part of the problem, I was just using these 3 numbers. Now these 3 numbers have 3, 3, and 3. So this answer has 3 sig figs, whereas this answer had 2. I know, that's really amazing if you're a science teacher. Okay, last question. How many grams? Whoa, we have not talked about grams at all. You're like, why are you asking how many grams are in something? We can't do that. Well, you do know how to find moles, and moles and grams are really related, so we know we're going to do something like that. So if I'm looking for moles, I need the ideal gas law. So first up in the ideal gas law, again, I'm going to be looking for pressure, volume, moles, R, and T. So let's go back to this. Pressure, that's going to be 1.25 ATM. There we are with that. Volume, 3.2 liters. Good. Equals The N, no, that's what we don't know. Okay, we think that if we find N, that will allow us to get the grams, though. The R, 0.0821. For sake of space, I'm going to cut those units out. I'm sorry, unit police. Sorry to upset you. I'm going to times by the temperature, 45. I cannot put 45. I got to put 45 plus 273, so I'm going to get 318 Kelvin. Now, I've got to solve for this, so 0.0821 on here, 318 Kelvin, there. Over here, 0.0821 and 318 Kelvin. I'm going to go ahead and do my math right here, and I'm going to get an answer that N equals 0.15321 moles. Now, I wrote a whole bunch of numbers out there. Do not cut this down to sig figs yet, because I need to use this to figure out how many grams of oxygen gas I'm going to have. I don't want to cut it short. I'm going to use sig figs at the end, but keep all these numbers. In fact, your calculator probably has more. So now I'm just going to do a mole problem. I've got 0.15321 moles of O2 over top of 1. And I've got to get rid of moles of O2, so I'm going to put moles of O2 on the bottom. I'm going to put grams of O2 on the top. And every time we have 1 mole of O2, we have about 32 grams. Remember, 16 plus 16. So I'm going to do this mole problem. The moles cancel out. I'm going to multiply those together, and with sig figs now, I'm going to get 4.9 grams of oxygen gas. I should have mentioned that. I know. You're like, why is he doing O2? Because oxygen gas is part of Hofbrinkel. Hofbrinkel are those diatomic molecules where they always combine in pairs. So H2O2, F2Br2, okay. So that's why oxygen gas was actually O2. 4.9 grams of O2. So that's it.